G'day, welcome back to Stiffy's Workshop. Today I'm going to be talking to you about the relationship between power and torque in an internal combustion engine. So these terms get thrown around. What do they mean? So they basically refer to how the engine operates and how the engine delivers its energy. So power is directly proportional to torque, and the speed of the engine, so the RPM of the engine. So if you've got a tachometer in your car, you'll be familiar with like RPM. So that's a direct measure of that. And so when we're trying to determine how a car is going to drive from a graph, so often you'll see a graph kind of like you have these pieces here, and you'll have RPM on this axis, and this will be the sort of the power curve. Will be the name of the graph, and you'll have different RPMs along the length of it, and you'll basically end up with two lines. So one of them will be the torque line. This one might be really flat, looks something like this, and then you'll also have a power curve on the same graph. And because this is a dead flat torque curve, it's going to be a dead flat power curve. So, and sometimes they're all wiggly, and sometimes there'll be holes in them, and they sometimes taper off at the end. But at its core, that's the sort of the different aspects of it. And up higher means more power, basically. So the confusion that gets thrown around a lot is, torque does something and power does something else, and I've got a really torquey motor, and that's all great. And that can be ways of describing how an engine delivers its torque. So, your really large capacity engine might have a lot of torque on the lower end and then have less up top, whereas a smaller capacity engine might have less torque overall, but may have a really consistent amount of torque throughout. And those they do change the characteristics of how it drives. In the case of a vehicle. But the key to interpreting it is to pretty much ignore the torque curve. So the torque isn't going to describe how the car actually drives. What actually matters is the power curve, and having power is the key there. So all torque is basically, you'll have, pretend that's a bolt or a drive shaft in the case of the car. And torque is, you've got a lever on the side of it. And, if we're talking about Newton meters, so that's Newton meters. What that refers to is a Newton, which is a measure of force, and a meter, which is a unit of distance. So let's say this lever here is a meter long, and this particular engine's making 400 newtons. It's pushing 400 newtons down on this. So on this is a 400 newton force, and that's 1 meter long. And as I'm sure you can appreciate, you're not going to go real far or real fast if that never moves, or it moves really, really, really slowly. It's just not going to do anything really for you. So that's where the RPM and the frequency of this Newton meter application of force comes into play. And, what does that mean for actually driving? So to move a mass, the distance, you need a force applied. If you just have a torque, you have 400 newton meters and no RPM, it's not going to go anywhere. Like, you could have 10,000 million newtons and no RPM, like no frequency, that's zero, then there's no motion. It's not going to do anything. You could have 10,000, but if it never does anything, it's not going anywhere. And conversely, if you have no force but you're applying it 100 million times a second, it's also not going to go anywhere. So what you need is some torque, some frequency, and that gives you the power. And the power is always what's doing the moving. If you don't have power, you don't have anything happening. You have more power, it's going to move faster. You can have a billion torque, but if you don't have the torque and the RPM, then nothing's going to happen. So I guess an example of that would be in terms of the math side of it. So if you're making 400 Newton meters, let's just say this for easy maths, kind of like I am in the orange car, so 400 Newton meters, and you're making that 400 Newton meters at 6,000 RPM, let's just say, and then you chuck in just a constant, which in this case is what's 2 kilowatts, so 9548.8 will give us kilowatts, and we ballpark it just approximately to 51 kilowatts. Cool. And so that's how much power you're making, and that's going to be the force accelerating the car. So you may have experienced before, if you increase the RPMs in your car, then it feels like you can push back into the seat harder. And so this torque and the increase in frequency gives you the more power, the more push. So kilowatts is push, and it'll also allow you to maintain a higher speed. So if you want to either increase the speed or maintain a high speed, then you want to make more power. So you're going to want more RPM out of your engine, depending on the characteristics of it. If it's not making any more power because you're just spinning it too hard, then don't do that either. That's not going to win for you. And for just to provide an example of the RPM difference. So we've got the same 400. Just keep the torque the same. So 400, and let's drop the RPM to 1500 RPM. And my engine wouldn't make 400 Newton meters at 1500 RPM. It just wouldn't work like that. It doesn't have the capacity for that. But let's say your engine did, and you're making all that torque right down there. Same constant, 954.8, and that's going to roughly be 62, a little over 62.8 kilowatts. So it's not the torque that's doing the pushing, it's this 62.8 kilowatts. And, the torque is part of this equation, it's part of what's going on, but the 62.8 kilowatts is what's driving you. So, yeah, that's what's doing the work, literally. And, in terms of practical applications of that, if you're trying to accelerate your car as fast as possible, or a motorbike, whatever it happens to be, and you know what the curve looks like. So let's say your curve looks something like this, the power curve. You might be able to find it, online or something like that, or if you have a good dyno chart, even better. Let's just say it looks something like this. And so because you've done your cool dyno chart, you've read this is RPM again. This is a power curve. This is your power curve, and everyone's going to look a bit different kind of thing, but that's fine. Got kilowatts increasing. So you want to drive your car with maximum sort of performance, and this is your engine characteristics, and you want to work out where you're going to get the most performance out of it. So you're starting in first gear kind of thing, taking off from whatever you're taking off from. So first gears first. So you're going to be starting off from effectively 0 RPM. You're going to have to, there's some slippage in the clutch, and if you have an auto transmission, there's slipping in the torque converter and that sort of thing, but effectively you're starting off at 0 RPM. So you're starting right down the bottom of this chart, so right down the back here. And first gear, you're going to have to be dragging yourself up. So you're going to want a fairly quick first gear so that you're not having to lug around in this low section before you really get into the power. So 0, and let's say this peak here is 251. Pulling that 251 out, and let's say it's 251 there. So we're trying to get up to, up into that power band. But then, we're still making pretty good power over here before it dies off, and we're still making pretty good power over here. So realistically, if we're running in that kind of area, we're making good power. So what that means is we can take it past our 6,000 because we know that that's 6,000 RPM where we're making 251. But, we don't want to be down here making 62.8 because we're going to drive real slow. And, just for argument's sake, let's say this power drops off at, 6.5, just say 6.5. 1,000 RPM, and down here is, easy maths, 5.5. 5,500 RPM is that. So we've got our 1,000 RPM sort of window here where we're making, the maximum amount of power, and it's, wide enough band that, things are going to work okay. So back to the gears. So first gear, we want to get first gear, and we want to take it all up to 6,500 RPM because that's going to get us the maximum time in the maximum amount of power range before it drops off. If we rev it to, 8,000, there's no power down here. It doesn't make any sense. The engine's not efficient at that point. So we're not going to take it to 8,000 RPM. If we could, there's no point. So we're changing to 6.5. Changing gear at 6.5. So first gear gets us from 0 to 6,500 RPM. That's first gear's job. And, speed is, that's a separate discussion. And then we're into second gear. And so, if we had, unlimited choice and we wanted to select a gearbox and we could pick every single ratio and we could pick so that everything would be perfect, in a perfect world, we wouldn't be coming back to 3,000 RPM because we've got no power there. It feels like the car's bogging down. So we'd try to get a gear that would then shift us back to 5.5. So then we want to go from 5.5. This is like perfect world stuff. We want to go from 5.5. We want to take it back up to 6.5. Bingo, bango. We're cruising. We're changing gears. Bang, back to 6.5. Third. Guess what we're going to do? 5.5 to 6.5. This is maximum power. So maximising power of the usage. And fourth, same deal. 5.5 to 6.5. Because we're going to set the gears so that they're in that position, and then we're going to be making the maximum power. So that's kind of how you use a power curve to get the maximum performance out of the car. And if your gears don't line up perfectly with this, then let's say your second to third leaves you going from 6,500 RPM, back to 4 or something like that. Well, if you're going to end up over here, then you might want to over rev a little bit. You want to take it a bit further past because that's going to, be basically the same thing. And then when you change gears, you back up into here, and then it's not going to bog down as much. You're back onto the power quicker. But ideally, you pick your gear ratios and then be able to do whatever you want. One thing I will say on torque, though, so we go over to the next page, and applications of torque. So torque curve, cool. Let's go on. And so your torque curve might look like, really low down here where the engine's not very efficient. Let's say it looks something like that. No, let's do something a bit more crazy, actually. Let's try again. So that'd be like a really well-tuned engine kind of thing. Let's say your torque curve looks like this. Cool. So torque curve. And RPM again. torque. Fantastic. So what you can see is this is the peak torque here. And, you know, for discussion, let's say that's at 400 Newton meters or whatever it happens to be. Let's say it's 400. Fantastic. So what torque actually measures is sort of the efficiency of the engine. So the engine becomes less efficient at higher RPM, you know, for whatever reason, it's less efficient at its lower RPM. So this sort of band here is where you're getting, you know, like the kind of peak efficiency range. So that's where the engine is converting, you know, fuel into power the most efficiently for that particular engine. And, you know, there's different loading characteristics. So, you know, it might be, you know, the engine's actually the most efficient. Like this is all wide open throttle measurements, I suppose. So you'd have to go a lot deeper into the testing to work out how it would work in real world conditions. But, you know, in general terms, wide open throttle is typically what you'll see in terms of a torque curve. If you're really, really into your efficient driving, what you would do is, or what you could do is you could go to a dyno center and dyno the car where you actually drive the car. So really sort of, you know, light throttle. And, you know, your torque curve might look like this, or it might look slightly different. And then you would target the highest point of torque to get the most efficiency out of the engine in terms of fuel economy, sort of thing. So if you're trying to increase the economy of your car and you need to get a curve like this at a low throttle position, because you typically drive at a fairly low throttle position, and then this would tell you where the most efficient point to drive your car is and when to shift gears, basically. So, you know, your car might be, well, you know, on the low end, you know, 2,000 RPM is really cool. And on the high end, you know, 3,100 is where I need to be shifting at. You know, because if I'm spinning more than that, then I'm going to be burning more petrol because I'm losing efficiency. So for me to get from A to B the most efficient way possible and using the minimum amount of petrol, I want to be using, or diesel, whatever your fuel source happens to be, then shifting between these points and maintaining the engine RPM between these points when I'm trying to, you know, get power out of the engine, then that's going to get you the most efficient way, because I know from the curve that at low RPM I'm not making power efficiently. You know, the engine's hardly keeping itself going, and at high RPM I'm just wasting energy spinning the engine for no reason. So that is a use for torque curves that you won't necessarily be able to pick out of a power curve, because power is obviously proportional to the speed as well. It's kind of it's an amalgamation of two changing things, whereas the torque curve is kind of its own thing. You know, it's a separate measurement, and yeah, one that can be of use in this regard. So hopefully that makes some sense between power and torque. Torque isn't how far you push it, as much as some people might tell you, and power isn't how fast you hit it. It's different to that. So all you're ever really feeling is the power, and the torque curve has an impact on, you know, how the engine delivers power. You know, it might, you know, some people really like having a very low RPM, you know, push, and, you know, that doesn't necessarily mean torque's doing the job. It just means the engine's very efficient at that low band. Whereas, you know, some motors you might have to spin on very, very high, you know, like a CB 250, you know, RR, you know, from the 90s kind of thing, 4-cylinder, 250cc motorbike, you know, to get its pittance of torque, you know, you might need to get to, you know, 16,000 RPM or 17,000 RPM, you know, which is just mental, to actually get some power out of it. But that's just it's a very small capacity engine, and it uses the RPM aspect of the torque curve or torque power curve to get its efficiency. So some ideas, and yeah, if you have any queries or, you know, things you want me to elaborate on, chuck a comment up, and thanks for watching. See you next time.